One more thing. So the site we call, the project we call COTRA, that is compartment transfer, because the MTBE benzene is we have seen that it's anaerobically, it's not degradable, but if you are bringing it to the oxygen, with the contact of oxygen, so in the aerobic environment, so it can be degradable. So that's why we say compartment transfer, for anaerobic to aerobic zone. Yeah, so welcome to the COTRA site.
What's the background of these producers?
Okay. Yeah. The whole site was, let's say, there was ammonia sulfate treatment unit, benzene distillation plant in 90s, and then in the 1945, during the Second World War, everything was destroyed. More or less 80,000 bombs were dropped in this area. So you can see all this new construction, but it was all gone during the World War. Then nowadays there are more or less like 200, 250 companies, new companies. They are working on different factories, industries, and more or less 10 to 15,000 workers are working. So it's a new site, but not only for that, the groundwater also contaminated due to accidental spill and some other actions because of the leakage of the pipelines and so on. So the whole area is contaminated. The main contaminations are MTBE and benzene that we have found.
So you also mentioned that there are contaminations by these high concentrations of ammonia due to the fact that they had here also ammonia.
Fertilizer production. And in general, the Ruhr region, Leipzig, Halle, Bitterfeld, from the historical point of view, the chemical industry was all based on lignite, brown coal. And brown coal was so cheap that you could produce very cheap electricity, and you could also produce more or less cheap coke. We had here in the nearby also chalk, so that we here in the nearby Leuna we produced carbide. From carbide you come to ethylene. With cheap electricity in Bitterfeld we produced cheap chlorine. And this is the chlorine and ethylene, we get then vinyl chloride, polyvinyl chloride, and so on. So all the things here was based more or less on the cheap lignite. We have also here nearby salt mines and chalk. Fortunately, in this region we have a lot of rivers and enough water. And if you flood such an excavated hole very fast, then you can suppress this process. But we have other regions in the more eastern part of Germany, Cottbus and so on, and they have not enough rivers. Then the natural flooding process takes about 20-30 years, and then you can imagine that you have a real leaching process, that the sulfitic compounds are oxidized.
Okay, so this
a lot of them with gravel, and then we have also some plant root mats. And our idea was, okay, soil filter, plant root mat. Why not to use a plant root mat as a root mat filter? Usually for those time we know already one user wrote a nice booklet about plant nets and so on. And then we thought, okay, if the plant root mat is swimming, then we have not so good treatment process because the water flows rapidly below the root mat. So we should realize that the root mat should sit on the bottom of the bottom. But it's a question of Brian, why each plant without gravel? How not to learn? Maybe we have some this here, so then we have such a kind of labor division, more or less technology development and so on is mainly focused in the UBZ, and we are more or less interested in the process understanding. What happens in our soil filters? So, for instance, we have here ammonium, and the question is, how is ammonium removed? What goes into the plant biomass? It is very easy to estimate, but what is the pathway of ammonium? Is ammonium oxidized to nitrite, nitrate, and then or is ammonium oxidized only to the nitrite? And then is the question, what happens with the nitrite? Is there a reduction with carbon source that we have also trinitrification in the classical aspect, or are the electron donors ammonium? So, and then we have the so-called anamox process. So for this, what to do? Calculations are not so easy. So we started with molecular biology, that we develop, we have fish probes, and then later we got the impression that it is better for quantification to use real-time PCR for quantifying copy numbers and so on. And as expected, we found anaerobic bacteria in our soil filter. Then the question is for us now, this anaerobic bacteria, they grow very slowly, they have a doubling time of 10 days or something, and it's a question how fast such a population is established within a constructed filter. My theory, it takes several years. In our laboratory scale system, we try to simulate it, and even if we try with a kind of inoculation. Usually in wastewater treatment plants, you never, for the exception that you inoculate something, maybe in anaerobic UASP reactors, this maybe something that in the future might be. We still are doing such experiments in laboratory scale. And if you are interested, then I can show you our laboratory scale systems. So then the next thing is also some extent for nitrogen that we apply nitrogen tracer experiments. So nitrogen 15 is relatively cheap, you can analyze, or we have even some colleagues in the Halle, they are doing for us the isotope fractionation analysis. So it means only to see how the natural abundancy of nitrogen 14 and 15 changes through by this low such a soil filter system. Then, for us also of interest is sulfate. So, horizontal filter is more unspecific for anaerobic than a vertical downflow filter. Here in this filter you have sensible investigate sulfate. In this horizontal flow filter it is very interesting. And it's also in our region, our drinking is relatively high in sulfate concentration, about 100 or up to 150 milligrams per liter. So it means it is a potential to produce in the ideal conversation up to 50 milligrams per liter H2 sulfide. So, and this is already a highly toxic concentration. We have investigated these processes in another fine system nearby Bodenfilter, which is now closed down. Here we have not so much this problem because the sulfate concentration is relatively low with about 10 milligrams per liter. So, but in case you have higher concentration, horizontal flow filter, you have to consider it. And we even measured high concentration of sulfide in such filters. So, and here we have also the possibility to use to characterize the natural abundancy, the distribution of sulfur 32, 34, how it changes, and then we could also show that in our horizontal filter the sulfate was reduced and partly in the further flow re-oxidized. And with such kind of analytical tools you can move such processes. So then another aspect is not our focus is on we have a lot of bacteria, and yesterday it was also started the discussion hygienization, why pathogenic bacteria disappears in our filters. Of course it is not a filtration process, but it is something else, and we assume that these are mainly based on microbial predatory activities. So it starts with bacteriophages. This you will find not so much in the literature about the whole and wastewater and bacteriophages. Then our hobby are the yellow meteorite microorganisms. If you look on a root net, then you have also a very high specific surface for attached growth. And maybe even a better surface because it is organic. Then you have the direct contact with the riser plane. It means it to the root surface, so that they can better profit from the carbon, the root exudates, and they can also better have access to the oxygen, which is also transported by the halophytes, the emergent water plants. But at the moment we have some problems and we need some advices from Mikey. So this is more or less something from my point of view. The more useful, interesting things you see then Katja will explain to you. We are more focused on process understanding, but as an engineer you can optimize the system. It's a very nice and it is almost sufficient. But we have the ambition to go and learn by better understanding and then have a better directed optimization of the process. But usually 90% of fundamental research will be not applied. So, but nevertheless, still I get my salary, I'm happy about it. And Katja supplies the UFZ with the successes. Yeah, some questions from the horizontal filter aspects. If not, I'm still here and I have also an email address, and we are interested in cooperation. Or later, or tomorrow, or next year.
Yeah. So water will flow from the top and below the top level, and then it will go down. And one of our idea was, first of all, we decided to run it individually. And this is the inflow groundwater concentration of MTB and benzene. Benzene is more or less like 14,000 microgram per liter. MTB nearly 3,000 microgram per liter. And after first stage, we can see that it is sufficient. Sometimes it's sufficient, but it's not stable. Sometimes it's, the value of MTB is increasing, and that's why we cannot rely on that results. And then we decided to combine them. It's a two-stage system. So this is the first stage, and this is the second stage. That's why we call it polishing filter. And we are also having willows on it. That you can see, these willow trees. And so there are some results. This is the inflow concentration. We are using different hydraulic loading rate here. This is the inflow concentration. So after the first stage, this is the outflow concentration of the roughing filter of MTB, and our drinking water level standard for Germany is 200. So after the second filter, after the polishing filter, all the values you can see lying below the limit value of drinking water. Same for benzene. This is the inflow. This is after the first stage. You can see the scattered results. Those are very unstable. But after the second filter, everything is below the 1 microgram per liter. It is really challengeable because you have to go down from 40,000 microgram per liter to 1. Sometimes the detection limit is, for the analytics is difficult. Another thing, so from this treatment performance, it is working fine. This is our investigation in the pilot scale. And another thing that we investigated, that as you can see that this is the plant with the air stripping with the activated carbon. We have calcium. From this context, precipitation is not occurring. For iron, this is the inflow and this is the outlet, so it's more or less like zero. So some iron are staying in the filter, but from clogging effect, we don't have any problem. Another interesting topic is what is happening in the winter time. So in our pilot scale investigation, when we were dealing with less hydraulic loading rate, then we see that this is the air temperature. You can see this is the air temperature, the green one, and this is the effluent temperature. That is what is inside the this is the air temperature. Sorry. And this is the relative concentration of MTBE. That is how far it is going up or down. As you can see, in the winter time, the MTBE is going up. So with a low hydraulic loading rate. And when we are increasing the hydraulic loading rate, we can see that even in the minus 15 degrees centigrade, the MTBE is below the level that we are looking for. So that means inside the filter, if you are putting more water, it's kind of like internal heating system. So the effluent is always at the 10 to 12 degrees centigrade. So outside temperature is not influencing the treatment efficiency. So from this context, we have seen that no precipitation of calcium or manganese, and we have seen the higher hydraulic loading rate is also beneficial for the treatment performance. And from this experience of 3 years, this is the second part of the mission. At the beginning, from the perspective of oxygen, this is very important and very interesting, because when one pulse is coming, the air inside is going out. So the air from the atmosphere is coming into the system, and this is important. And when it goes down, and before the next loading, this air is entrapped into the system, and that's what the microbiology will look at.
How much is loaded?
Now it is 960, kind of like one per day, per meter square per day. Yeah. This is only for the smaller system. And later you will see that in the bigger plant we are treating nowadays 60 cubic meter per day. So it's a huge amount of water. And more or less, if you want to clean the whole area, you have to clean, let's say, 600 cubic meter per day. So we have to install more of the system. You'll see later. Yeah. Yeah, that's. So if you have some question, then you have to answer.
How deep do you extract
very. I don't know, until we get the water. And well, first of all, we have several oil there, and we are extracting that water and giving it to this white. You can see where the poster is. So the water is coming here. How deep the water we are, I really don't know. But we are bringing directly from the ground, and from that well pumping to here and directly to the bottom, and then to our filter. So another interesting question that I asked when I first started working here, why we are using different material? Why expanded clay? Why not simple material? Let's say if you want to construct such a system in other countries, developing countries, probably this material is expensive. What about gravel and sand? Normal gravel, normal sand. That's what we did. This is our gravel filter. You can, on the top, we are still using the expanded clay, but in the main filter there is normal gravel, 3 to 6 millimeter. And the last one is the sand filter, normal sand. And the results are more or less similar. More or less similar, and let's say you can say 3%. let's say 0 to 3, 0 to 5. We are using the same size like zeolite and normal sand and expanded clay and normal gravel. 3 to 6.
Then you use the sand filter only as a second.
You can say that. Yeah, but only with the vertical. Yeah, vertical sand filter you can say.
And they're not planted.
That was also interesting thing because until now we haven't seen the influence of plants. Of course they are putting some oxygen, this and that, we know that. But until now we haven't found any difference. So that's why we have this second stage plants, and we are now getting the results. And then probably in a few months or in a few days we will also put some plants and have some results. And then make a difference whether there are some significant difference between plants and without plants. Probably not. Probably get a comparison. I mean, these are just like our research site. We can play around, we can change the loading rate, we can put this plant, that plant. But for the bigger site, we have decided because the company, they like the system that works. That is, they said that we will just scale it up. Whatever it is, same material, same plant, same whatever. So, we will see this. And the loading rate that we are using is just upgrade it to the area. And willow plant, exactly the same. Even if we are saying that probably willow we can forget or probably no plant. They say no, we will do exactly what we have done, and then this will be kind of like a real flushing out. So
You have no idea how much water is taken up.
it's because we are using, let's say 1,000 more or less like 1,000 meter per day. So it's huge amount of water is coming. So if some rainfall is coming, it's very so
Going so fast.
even if let's say 2 millimeter or even 2 centimeter of rain, it's
Makes sense.
yeah. But Peter is having the key, and Peter is responsible to take care of that side. So and they're having a meeting. Manfred and
Yeah, but I mean, should we just
okay, then we can we just a rough idea we can give, and then we just have a look here. So we can please come here and for our safety purpose and for our interest, we put a sedimentation tank in the middle just to see if there's some precipitation of iron or any other ions that we can catch, and we can quantify how much is going out after the first filter. And this water is pumped to the second filter, the pollution filter, and same happening, water is flowing down and coming to the collection tank, and from that collection tank it is going to the reinfiltration of groundwater. That means the water that you are getting, you can directly infiltrate into the ground where it is not even contaminated. So it's similar, but the benzene and MTB in the inflow concentration is relatively low there, but still at the end we are getting MTB of 43 plus minus microgram per liter and benzene 0.4 microgram per liter. This is how it is working, and I'm showing you the results of last 1.5 year. And definitely, as we have already talked about, if emission is not playing a role, so definitely where the microbes are, where the MTB and benzene are going, microbial degradation, that's what's happening. So MTB and benzene are degraded, and oxygen is coming in and carbon dioxide is going out. From the emission perspective, as I told that the top layer is acting like a air biofilter, so some biodegradation can also take place. MTB and benzene can also biodegrade in the top layer, so that nothing is coming out of the system. From the influent and effluent, you can see the calcium is the results of last year. So what's coming in, that is going out. So flushing of the calcium, so there is no precipitation. The similar thing for temperature, even in the minus 21 degrees centigrade, you can see the effluent temperature is 13 degrees. So it really doesn't matter whether you are doing it in Russia or Germany, the cold countries. It will not affect your filter system. So this is what you can this you cannot see because of the cover layer. We'll cover it. So you will even now you cannot see what is going to be happening in the below. But this is what we have done, and now this is our product. We have already okay, not because we are a research institute, we cannot make a business, but Bauer was interested to scale it up, and they did. And yeah, with the local authority, water is getting let's say MTBE and benzene free, so you can re-inject this water even in the non-contaminated aquifer. So life is more or less easy. And from that perspective of activated carbon with the precipitation, and because it's less expensive and easy to handle, not like the system that already exists in conventional system. Yeah.
So 2 years ago they built the first upscale plant.
Yeah, 1.5 years.
And what volume again is it doing?
60 cubic meter per day.
And now there's a tendering process to
for the remaining. So at least 600 cubic meter per day you have to treat to get the whole area to aquifer to treat. And so another 4 or 5 probably. Yeah. It depends on the design.
Yeah.
Probably we can make it bigger.
And at the moment there's a process going on with commercial partners tendering to do the upscaling.
Yeah, exactly.
So in the next year it will be built out at this.
Yeah. So you can see one.
And the construction work going on now?
Yeah.
Is it already for preparing the site, or?
No, one filter, one setup is already there. You can see this, and the others they are on the phase, tendering phase and construction phase. So it will be ready probably in 1 year.
Okay, so it's already started the construction.
Yeah. It's already at the
Because you said the tendering is going on, so I'm just wondering what they're already constructing.
No. Yeah? Someone else? Something to drink? No. Just to smell. If anybody interested, just to smell the inflow water, the smell of benzene.
Oh, it's benzene, not MTBE?
Yeah, of course, benzene. Sorry?
Is it the same glass?
No, it's different. We're using blue or green for the effluent, red for the influent, so that we're not mixing it up.
A new, ecotechnology plant, and fortunately we managed this. So then, what did you mention about the the wall in the ground?
Yeah.
The water? Yeah, more or less.
Yeah.
Okay.
Where the water is coming from,
Yeah.
But one question was how deep the water we're extracting from. I mean.
Yes, the groundwater layer is between around 8 and now it's beginning in 6 meters of depth, and it's like 4 meters, so between 6 and 10 meters more or less is where the main groundwater layer is situated, and it is what is also interesting, or was interesting, when they put this barrier, this wall. It was the first time to be realized a wall made out of the material from the ground itself. It's a kind of machine which is
Drilling.
yeah, it's like drilling, but it's not really drilling. It's another technique. I don't know the English word. Like fräsen, I don't know if somebody knows.
Like
so it's going down and then making always some 3 meters of drill, and going up some kind of concrete liquid is injected, and with the same stone and soil material they make a very safe water barrier, wall protection. And this was first realized as a technology offered and also developed by Bauer Umwelt GmbH, who is also the company what is running this plant at the moment, and what is amongst others applying to construct the big pilot scale plant. So we get the groundwater from the same wells. There are 4 wells in different places in front of this wall to get the groundwater up. We get it from the technical plant, for this technical scale pilot module, and we treat between 10 and 20% already is treated. 10 and 20% of the total water certain amount, sometimes even a bit more, because depending on the stage or on the operation state. In this plant, it was run between 100% usual long-term load, and then there have been done experiments over a lot of months with the double load. So the normal is 1000 liters per square meter a day, or 1000 millimeters per day in the first roughing filter, and in the second filter is 500, half of this load. This is the pumping station. There's a little pump inside. It's perhaps difficult to go everybody. When we come back down, if somebody wants to have a look, just go in. There's no safety danger or something. So this is what we see here. Hopefully we will see a load in some, loading in, no, it's every 15 minutes, but I can have a look soon. So
I had my show this morning, thank you.
What we see here first is our emission protection layer, which is the top layer, we call it top layer, which is expanded clay, a clay material. There are different industrial products like very round, or this is the less expensive version, which is just irregular form size. It's very light, so it's very porous, and it's collecting, absorbing water. So the raw white is very little, but when it is wet, it is quite more heavy. And the advantage is, like it is always wet, the biofilter effects are not lost so quickly when the sun is coming or something. What we see here is
the main filter layer.
Yeah, the main filter layer is it's also an expanded clay,
The lower size.
but between 3 and 6 millimeters. Right, so find some.
Sand under it.
No,
What we see here
clay, but smaller, I think.
is one of the effects to be done in this filter stage. We have a groundwater containing quite a lot of, more or less, between 5 or 4 and 6 milligrams per liter iron. So the roughing filter is for oxygen uptake, and within this process, the iron, of course, is from iron 2 is changing to iron 3, and we get an iron sludge, which is collected here. And as far as the filter material is more or less satisfied with iron, it is flashed out. It should be flashed out with the drainage down in the filter and going to the sedimentation tank, which is just this blue tank, blue container we see in the back. Until right now, like almost 2 years of operation, still the filter is collecting iron, still not leaving the filter. So the sedimentation is still waiting to be necessary to start working.
How big is the stones under this layer?
3 to 6 millimeters.
3 to 6.
3 to 6, okay.
And the top one is
The idea is, or the question why, it's a little difficult. I forgot to bring a material sample. It's like this small corn.
Yeah. Okay.
It's like this is a round corn, but it's all between those two corns. It's the smallest and the biggest one, more or less. It's like this, no? And Then we have our irrigation system, which is you see more or less 50 centimeters of space between the tubes. It's like a cam. I don't know in English. Yeah. We have the main distribution tube, and then the small tubes are distributed by this way. When we are now, meanwhile, waiting for the load to see how it works, we can just look around. And
did you explain the emission tests we did?
No, I did not. Did you talk about emission measurement? Yeah, he explained over there. Yeah. So
Okay.
we did some point emission measurement with directly with a gas chromatograph measuring. Yeah, no online, but directly from on the place, on site. We had the gas chromatograph here and we measured and found very low emissions. What we found in the experiments over there, he told probably, is that without layer there is quite a big emission, and with the top layer emission is almost zero. To prove that it's really important to have this protection.
Is the smaller one under? Is it also expanded clay?
Yes.
Is it cheaper than the normal small stones?
No, the expanded clay of course is a variable expensive material.
Yeah.
But it is well known to be very effective for filtration, for water filtration. Or biological degradation. That's why it was originally chosen. It was the load and the concentration of contamination was in the beginning of the experiments was over there 20,000 micrograms benzene and around 5, 6, 8,000 micrograms containing were not any results from research or experiments before how to degrade this water. Of course, it was known that there is a biodegradation with oxygen, so it was decided to use this material. What we meanwhile did, we did parallel experiments with normal gravel and sand, and we found that it's what is to be seen is that in the starting phase, it's taking more time for the adsorptive and water capacity, holding specialties of this material. Obviously, probably
Goes to
get started faster.
Yeah. It starts faster here to grow.
Huh?
The biofilm starts faster to grow on this.
Yes. It was we did when we initiated these two filter systems, the startup period to get really good cleaning effects was between more or less 1 month, and it was working in perfect way already.
And the sand and stone was later on. It took longer time for the sand.
Yes. It seemed we have not directly direct comparison between both systems because we did the experiments in different periods of the year, times of the year, so it's not absolutely sure, but it seems that probably with this material it is somehow faster. And also the zeolite in the, we see now the polishing filter, second stage, is also covered with this protection against emission. Also in this two-stage system there is almost no emission possible anymore because the concentration is already quite low, and so the emission risk is not really high. And then we have I can open a place to show the zeolite soil as well. I think we did not see it over there. Yeah, and hopefully there's a lot right now. What we see over there is all this side in former times was a filling stage for oils and carbon, hydrocarbons, and so within 50 years of history, was a lot of contamination in the soil because of accidents or Second World War bombing probably, but more in the center of this industrial part, and so they are now still taking the contaminated soil out, bring it to a soil treatment plant or to deposit it. There is an intermediate storage of soil material which is not contaminated but later to be used. And in this area, what we see here, starting from more or less the middle of July, the big scale plant with this technology will be constructed. 3 months. Probably starting operation in October or something like this.
You said it is BTEX though. It's not just benzene, it's BTEX.
We have mostly benzene, biggest part. Sometimes when they were changing some remediation works within the industrial zone still, there is more influence. Or also when the groundwater is moved and they did some soil excavations, we had BTEX.
But you're not finding toluene or benzene or xylene in your...
Also, but
it's low enough, it doesn't matter.
No, it is degraded as well.
Okay.
It's degraded.
Just didn't really any value.
Yeah.
So it is above your limit, it's above your drinking water limit. What's coming in?
No, what's coming in is all degraded in the system in the biological.
No, and then in the groundwater. Then.
Yeah.
Your toluene and the benzene or xylene is above your drinking water limit.
Yes.
Okay. But it's treated the same way as benzene.
All this group of without problems. This is yeah. That's why more or less the filtration system has to be in a reachable way to be maintained.
And most of those...
So that's why the authority who is doing this construction or is financing from the state of Saxony-Anhalt, they decided to let it without the willows. Also the willows look nice, and you have seen over there it's quite green, it's like a biotope as well, but for operational maintenance costs it's better without.
And then you literally take it everywhere. The problem is though, expanding municipalities.
Yes, this is another advantage. There are like 4 or 3 advantages. One is by the emission because of the wet material. No? The other is to be removed easily. No? Or no, second would be thermal protection also, so that it's not too getting too cold in winter time, because the part of the material which is dry, it's also good isolation. And also, if there is snow or ice, the upper part is freezing first, the upper 5-10 centimeters, and below it's like a cover. Also, we had no problems with the oxygen. Also, if it is covered with snow or ice, oxygen is still getting in.
They do use them.
You could say that it is all covered with ice, so the oxygen is missing.
Sorry guys.
So
we can keep talking as we walk.
We have to go this way again.
From all of the 15 systems at the site, and generally that happens on Tuesdays. We come in the morning, we take the samples, we measure field measurements such as DO, pH, temperature redox. We do all that on site here. And we pack up all the samples in ice boxes and take them back to UFZ, where we continue the rest of our water quality analysis. So all of the analysis takes place on the same day that the samples were taken. And we've been monitoring the systems for BOD, TSS, TOC, TN, ammonium, nitrate, nitrite, turbidity, and E. coli. And so our current database is kind of these basic water quality parameters. We've started some collaborations with a group from Peter Kuschk in looking into pharmaceutical removal in some select systems. I don't have any of that data yet. His students are still working on it, but we're working on increasing the collaboration between our two departments, as well as looking into some more microbiological investigations. Running. There's a diaphragm pump. You'll hear it. It kind of sounds quack, 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 quack. You'll hear it, and it basically, when the windmill is running, it's actually pushing air into the system actively. When there is no wind, there is no air going into the system. So it's one of the drawbacks, but it's the first windmill aeration system ever, so you got to start somewhere. We've gotten the signal. We can go.
Pamela? Okay. You can...
Wetlands, and the focus gonna be the difference in the quality by different loading regimes, and also clogging issue. You can see that the soil is quite like loamy sandy soil, and the permeability we found out is quite low, so it might be interesting. We just took the local soil here, and which replicates, like in developing country, always the situation where we just have to deal with the local material. And we're gonna also
explain some of her PhD work too. Originally, these were individual, unsaturated vertical flow systems. We've got a 4 to 8 millimeter pea gravel unplanted system. This is a 1 to 3 millimeter sand. In the earlier group, they said that's not a sand, that's a fine gravel. So take it as you will, but it's a much finer material. This is typically the type of sand that you would use in the United States for a vertical flow sand filter. The original, 2 years operation of these systems, they were 4 individual systems. And one of the reasons we chose the pea gravel to include in this mix of different designs and systems was our work in Jordan. It's really hard to find sand in the desert. And for treatment wetlands, it's really a problem. Dion, who was in the last group, he actually was importing sand into Saudi Arabia or someplace like this because it's that difficult to find well-graded, well-washed sand for vertical flow filters. What we found in Jordan was a similar grain size in this 4 to 8 millimeter range, but it was made from a zeotuff, more of a volcanic origin material. And one of our original research questions was, okay, if you've got the same design, what's the impact of the grain size on the treatment performance? Can you still get good treatment if you've got a bigger grain size, if that's what's locally available? Because it's always more advantageous to use locally available materials when you can, rather than shipping things across the world just for a one-time installation. Now, the systems are combined in, we've got first stage and second stage systems. So here you see the unplanted 2-stage system. Behind me is the first stage, second stage of the planted system. And Heide, do you want to talk about a little bit of what your research is now?
Yeah, thank you, Jenny. Well, as Jenny told us, this system consists of 2 beds, a gravel connected with sand filter, and basically we put it like a planted one and unplanted one to make a comparison between plants' role in each bed, even there is no significant role for the plant. As well, I have internal samples at different depths, like profile depth. We can see it in these pieces to illustrate the rule, the treatment process during depth, when the water filtrates in this filter to show the process of treatment. As well, my research is focusing on how to optimize the nitrogen and pathogens removal using vertical constructed wetland in Jordan and Germany. So we are working now in modification. I spent the first year in my research only monitoring the system as it is. Last week we did something like modification in this system. We tried to make a saturated bed or half saturated bed in gravel, so we can enhance the denitrification process, so we can reduce the nitrogen. Yeah. And this is also we are have two systems in Jordan, but one of them is two-stage, multi-stage, and another one recirculation system. And as well, I'm working on modify this system to meet the Jordanian standards for reuse. Yeah, thank you.
Thanks, Haida. Haida mentioned the internal sampling for these systems. What we have installed in each of these systems is a pan lysimeter. This is what it looks like. They've been installed at 3 different depths. Here you can see 10 centimeters, 20 centimeters, and 40 centimeters down into the bed. So we're getting a nice profile of that first part of the bed where most of the biological activity is. The pans are installed just underneath this last bit of the bed here. And what we've done is we filled it with coarse gravel. There's a tube that connects the pan to this outlet chamber here. And so when the bed is dosed, water falls in, we catch a small portion of it, and we can collect the sample. And so it's analogous to a grab sample. It's just whatever's falling through the system right after a dose. And you can see some of the profiles here behind you in the bottles. Feel free to pick them up and shake them a little bit, but here's the actual profile for the whole two-stage system, and you can see the difference in water quality, at least in the gravel system. By about 20-40 centimeters, you've got completely clear water.
Where are they situated specifically?
You can see the outlet.
Yeah, if we come over here, basically there's one pan located here, 10 centimeters down, one here, 20 centimeters down, and one here, 40 centimeters down.
The edge.
It's actually still under the distribution system, so we can actually catch some water. And then there's tubes here where we can, in this outlet chamber, you can look at that one as well, basically connecting at the 3 different depths. So we basically take the tubes out and just put a bottle underneath and can collect from inside the system.
And so they're situated
like
that.
Literally like this, just 10 centimeters down.
So about 5 centimeters, 10 centimeters, 15 centimeters in from the edge?
It's about here, so maybe it's more like 30.
How much water you get at one dosing?
One dose, it really depends on the day and the system, but you can get 300 mils in a dose.
Yeah, but you join the sample in 3?
No, they're separate.
All 9 are separate?
No, there's only 3.
You only have 3?
Only 3. So all
in our
3.
system we have 9.
Yeah, you've got 9, and you've got a different mechanism. You've got a bottle that you go and empty. You let it fill back in, which is more of a composite sample approach, and then you take your water from there. Yeah.
And we have 9, and we have seen performance differences in the bed.
Within the bed, yeah. Start to look into various optimization.
It would be interesting to make the same scheme now with the planted system. See if they get yellow.
See if it's see if they get yellow.
For the yellow weed bag. Yeah, but also here I think it's also related to change of conditions.
Yeah, so you think
in the environment,
yeah.
get under stress.
Yeah.
It would be
interesting, yeah.
Just to see how.
Well, what would be interesting, yeah, is to flip the aeration scheme. So put this one on 24 hours a day, put that on the intermittent aeration, and see if you do get the same water quality in the end.
Yeah. This is something to run it longer and see what happens.
Yeah. Yeah. But right now these have been operating. This planted system has been operating since day 1, steady state. Yeah. So we haven't made any changes.
Why is it double?
But you can see some stress here on the systems. But yeah, it's just this little one. But if you want to see some stress phragmites, please walk this way. The system is under 24 hours electric air pump. The unplanted system right now is connected to our noisy little friend up there. running like it is now, there's some air being delivered to the aeration system in the bottom of the bed. When there's no wind, there's no aeration being delivered, and so of course you don't have quite the treatment performance that you do in the fully aerated.
Periods without wind. A little bit of wind most of the time.
Well, we tried to actually quantify the airflow measurement from the windmill. That we took 2 separate weeks last summer, and there was no wind. We couldn't get the measurements because we had rented this machine for like 1 week, and there was no wind. Unbelievable. So yeah, we do get periods of no wind. We do come out here, and he's not running, and when that does happen, you see it directly in the water quality. The water is much cloudier, much darker, smells worse than it usually does. Whereas the fully aerated system, the water you can see is crystal clear, doesn't smell, doesn't really even look like wastewater anymore. The windmill is only on the unplanted system. So.
Is the same type of everything for the aeration?
Yeah, the exact same tubing. Really, the only difference in physical design between these systems and the vertical systems over there is the flow direction.
And the windmill, you bought it or you constructed it?
We bought the windmill. We had to construct it, and yeah, it's basically it's a windmill that can generally be used or generally sold to farmers who have like a pond on, and they just want to aerate the pond a little bit on their property.
Okay, so the diaphragm with the pump was coming.
The whole kit came together. Yeah. So. Yeah, I think so. Yeah, I think that's a typical application. This is the first one ever connected to a wetland system.
You don't have a pattern on that?
Nope.
Okay.
What is the difference in quality?
The difference in quality between these two beds? It's huge. Basically, we're taking all the BID, all of the ammonia out of this system. E. coli concentrations are below 200. Total nitrogen removal, we've got about 70 going in and maybe 40 coming out on this end. For the windmill system, we don't have any total nitrogen removal. We're actually limited. Right now, they're running at the same flow rate. So the first step was let's just replace the air pump with a windmill pump. So we're not getting any total nitrogen removal right now from the windmill system. E. coli removal isn't great, but if you look at the water, maybe a little bit, but not much. Yeah.
So you said that the total nitrogen reduction and the coli reduction are somewhat related. You said you got better nitrogen or total nitrogen reduction and better E. coli reduction.
In the fully aerated system, but I think it's due to this fact that the system is number one fully aerated, and then you've got this gradient of redox and environmental conditions in the horizontal flow systems.
I agree. I'm just wondering about the E. coli and the raising the population.
Yeah. I mean there could be something. Okay. And so that's the same for all of the systems here. Okay. It's not pretty, but it works.
It's pretty